planet so large, 7 Jupiters could fit across its middle, a world boiling alive, losing its own atmosphere into space, and a giant so far from its star that 1 year takes 2,000 of ours. We found them, and they terrify scientists. Tonight we travel through 3 of the most extreme planets ever discovered, worlds that glow from the inside, rain liquid glass, and get swallowed by their own stars. If you enjoy this journey, subscribe and drop a like. Let's go. For most of human history, we assumed every solar system looked like ours. Small rocky planets close to the centre, gas giants further out, everything neat, everything ordered. That assumption felt safe. It felt logical, and for centuries, nobody had any reason to question it. Then in 1995, everything changed. A team of astronomers in Switzerland pointed their telescope at a star called 51 Pegasi, about 50 light-years from Earth. They were looking for the tiny wobble a planet causes when it tugs on its star with gravity. The method worked. They found a planet, but what came back from their instruments made no sense at all. The planet was roughly half the mass of Jupiter. That part was manageable. What broke everyone's brain was its orbit. This thing was circling its star in just 4 days. 4 days for an entire year. Our own planet takes 365. Even Mercury, the closest planet to our star, takes 88 days. For a planet that size to orbit that fast, it had to be sitting almost on top of its star. The distance between them was about 100 times closer than Earth is to our own star. At that range, the heat would be unbridgeable. Thousands of degrees. The planet should have been cooked down to nothing. Scientists called it a hot Jupiter, and they had no model that explained how it got there. Their best theories said giant planets could only form far from a star, where it's cold enough for gas and ice to clump together. A gas giant that close was a physical contradiction, according to every textbook in every university on Earth. And that was just the first one. Over the next decade, telescopes found dozens of hot Jupiters. Then hundreds, each one sitting in places where no planet was supposed to exist. Each one challenging the idea that we had figured out how solar systems worked. Scientists scrambled to rebuild their models from scratch. Here is what made it even stranger. Some of these planets were bigger than Jupiter. A lot bigger. Jupiter itself is already 11 times wider than Earth. You could fit over 1,300 Earths inside it and still have room. But astronomers started finding worlds that made Jupiter look like a pebble. They found planets 2 times the size of Jupiter, then 2.5 times. The instruments kept pushing further. Each discovery landed like a punch to the gut of every planetary scientist who had spent years building computer models of how planets form. The universe, it turned out, had spent billions of years building planets in ways nobody had imagined. And here is the part that still keeps researchers up at night. These massive worlds do damage. When a giant planet forms or migrates through a solar system, it throws everything else around. Smaller planets get flung out into deep space. Rocky worlds that might have hosted water, maybe even life, get shattered or ejected entirely. The gentle, balanced system we live in looks increasingly rare. Every time we find one of these giants, we understand a little more about how violent the universe truly is. The benchmark for measuring all of them is Jupiter, and understanding just how extreme Jupiter itself is will make what comes next feel even more impossible. Jupiter is the biggest planet in our solar system. You already know that. But knowing the label and actually feeling the scale are 2 completely different things. Picture the Earth as a grape, a single grape sitting on a table. Now picture Jupiter next to it. Jupiter would be a basketball. 11 grapes lined up in a row would fit across the face of that basketball. Over 1,300 grapes would fill it completely. That is the size difference between our planet and the largest world orbiting our star. Jupiter is so massive that its gravity controls the entire outer solar system. It flings comets away before they can reach the inner planets. It has been doing this for billions of years, acting like a giant shield. Some scientists argue that without Jupiter intercepting debris, Earth would be hit by catastrophic impacts so often that complex life would never have had time to develop. The planet spins faster than anything else in our solar system. One day on Jupiter lasts less than 10 hours. That spin is violent enough to create permanent storms. The Great Red Spot, a storm wider than the entire Earth, has been raging for at least 350 years. Scientists are not sure it will ever stop. Its magnetic field is the strongest of any planet we know, 14 times stronger than Earth's. That field extends outward for millions of miles in every direction, creating a region of trapped radiation so intense that any spacecraft flying through it gets bombarded like it is standing next to a nuclear reactor. Now here is where the benchmarks start to break. Astronomers use Jupiter as the measuring unit for giant exoplanets, the same way we use miles or kilograms. They say a planet is 1 Jupiter mass, 2 Jupiter masses, 10 Jupiter masses. It is the yardstick for the outer edge of planetary science. And some of the planets we have found blow that yardstick apart. When a planet reaches 13 times the mass of Jupiter, something extraordinary happens. The pressure inside its core becomes so intense that hydrogen atoms begin to fuse together. That process releases energy, a lot of energy. Suddenly the object stops behaving like a planet and starts behaving like a dim, failed star. Scientists call these objects brown dwarfs. The space between a regular giant planet and a brown dwarf is one of the most contested zones in astronomy. Researchers argue constantly about where the boundary sits and what rules define it. And sitting right in the middle of that argument is one of the most extreme objects ever found. An object so large that scientists still debate whether it counts as a planet at all. Its mass is somewhere between 15 and 20 times that of Jupiter. Its width is staggering enough that 7 Jupiters would fit side by side across its equator. If you replaced Jupiter in our solar system with this object, its gravity would reshape every orbit in the solar system. The inner planets would be flung into new paths or ejected entirely. It sits 359 light-years away, buried in a swirling disk of dust and gas, still forming, still growing, and still generating more heat than almost any planet scientists have ever measured. Its name is HD 100,546b, and it is unlike anything in your frame of reference. 359 light-years from Earth, something massive is being born. 1 light-year is about 6 trillion miles. 359 of them stacked together puts this object so far away that the light leaving it right now will not reach your eyes for 359 years. By the time that light arrives, every person alive today will be gone. And yet astronomers have measured it. They have estimated its width, its mass, its temperature, and its behaviour. The numbers they came back with forced some of them to double-check their instruments. The diameter of this world is estimated at over 600,000 miles. For comparison, the Earth is about 8,000 miles wide. If you drove a car at highway speed without stopping, crossing Earth's diameter would take about 5 days. Crossing this planet's diameter would take over 10 years of non-stop driving. The scale is genuinely hard to hold in your head. 7 Jupiters would fit side by side across its middle. 7 of the biggest planets in our solar system lined up in a row, and they would barely stretch from one edge to the other. Now consider the mass. Mass is different from size. Something can be large but light, like a balloon. Something can be small but heavy, like a brick. This world carries an estimated 15 to 20 times the mass of Jupiter. That means it is pulling on everything around it with a gravitational force of 15 to 20 Jupiters stacked together. At those numbers, it sits in a zone that scientists call contested. The current scientific threshold for a planet's upper mass limit sits around 13 Jupiter masses. Anything above that starts fusing hydrogen inside its core and becomes a brown dwarf. This object clears that threshold with room to spare, somewhere between 15 and 20 times Jupiter's mass, depending on which measurement team you ask. So is it a planet? Is it a brown dwarf? Scientists have been arguing about this since the first observations were published. The answer depends on how it formed, and that question opens a completely separate debate. What everyone agrees on is the environment it lives in. It orbits a young star surrounded by a massive spinning disk of dust and gas. That disk is a construction zone. Planets are still being built inside it. The disk stretches outward in a flat spiral, thick with material, and this enormous world sits embedded inside it, hoovering up gas and dust continuously, still adding to its own mass. Think of it like a storm drain in the middle of a flooded parking lot. Everything in the disk near its orbit gets pulled inward toward it, sucked into its gravitational grip, and added to the growing mass of the planet. It has been doing this for millions of years. What astronomers still cannot agree on is whether this object grew slowly from a seed of rock and ice the way regular planets form, or whether it collapsed all at once from a massive pocket of gas the way stars form. The method of birth changes its classification entirely. Either way, what is sitting out there right now is immense, violent, and still growing. And the reason it glows in the dark is even stranger than its size. Most planets we study are finished products. They formed billions of years ago. The chaos of their birth cooled down. Their surfaces or atmospheres settled into whatever they are now. When we study Jupiter or Saturn, we are looking at ancient objects that have had 4.5 billion years to stabilize. HD 100,546b has had less than 10 million years. 10 million years sounds long, but in cosmic time, it is nothing. Our galaxy is 13 billion years old. 10 million years is like the first 3 minutes of a full school day. This planet is a newborn, and its birth is still happening right now, in real time, as you listen to this. That changes everything about how it behaves. Because the planet is still actively pulling in material from the disk around its star, it is experiencing constant infall. Streams of gas and dust spiral down toward the planet from the disk above and below it. As that material falls, it picks up speed. When it crashes into the upper layers of the planet, the collision converts that speed into heat. Enormous amounts of heat. The kind of heat that makes the planet glow. This process is called accretion. Every large object in space that is still gathering material goes through it. But the scale happening here is extraordinary. The planet is not gently drifting through a thin cloud of particles. It is sitting in the middle of a thick, dense disk, pulling in material across millions of miles of space. Picture a whirlpool in a river. Now make that whirlpool the size of a solar system, and make the thing at the centre a world larger than 7 Jupiters laid side by side. The swirling material does not drip in gently. It smashes in at tremendous speed. Each impact adds energy. Each stream of falling gas raises the temperature of the outer layers. The planet has essentially been running this violent process for 10 million years without a break. And it shows. Scientists estimate the temperatures in and around the forming planet are extraordinary, well beyond what any normal gas giant reaches. The outer regions glow with infrared light that telescopes can detect even across 359 light-years of space. There is something almost alive about the image. A dark, churning world in the centre of a glowing disk, constantly feeding, constantly growing, constantly generating heat from the violence of its own birth. But accretion is only part of the story. The material falling into the planet does not arrive evenly. It comes in streams and clumps. Some moments see heavier infall, some moments see less. The result is that the planet's luminosity, the amount of light it puts out, fluctuates, it brightens and dims over time as the feeding process shifts. Astronomers have watched this happen across multiple observations. That behaviour matters because it is one of the strongest clues scientists use when trying to understand what this object actually is and how it formed. A planet that forms by slowly building up rocky material should not glow like this. The glow points toward a more chaotic, rapid formation. And a rapid formation changes everything about what this object might become. The internal heat it generates tells a story even more extreme than the formation process itself. Most planets in our solar system are cold inside relative to stars. Jupiter has a warm core, somewhere around 40,000 degrees at the very centre due to pressure and leftover heat from its own formation. But that heat stays buried. Jupiter's outer atmosphere drops to around minus 160 degrees. The inside stays hot, the outside stays cold. The heat radiates out slowly over billions of years. HD 100,546b does the opposite of slowly. Because it is still actively forming, it has two separate heat sources stacking on top of each other. The first is the heat of accretion. Material falling from the disk crashes into the planet's outer layers and dumps kinetic energy as heat. The second source is internal. A world with 15 to 20 times Jupiter's mass generates gravitational compression at levels that produce significant internal heat on their own, completely separate from anything falling onto it from outside. These two sources combine, and the result is a planet that radiates heat outwards so intensely that it becomes detectable as a glowing object in infrared light across 359 light-years of space. Infrared light is the kind of light your body gives off. Every warm object radiates it. The warmer the object, the more infrared light it emits. When a telescope tuned to infrared points at the star system containing this planet, it picks up a separate glow coming from the planet's location. A glow strong enough to detect across a distance so vast that the light takes 359 years to arrive. Scientists have described this object as glowing a dull, deep red in the darkness of space. Picture a coal in a fire that has burned down past its peak, but still radiates heat in every direction. The ember does not flame, it glows. That is the visual equivalent of what is happening here, except the coal is larger than 600,000 miles across. Here is where the internal heat leads to something even more unsettling. Objects that generate their own heat internally, as opposed to just absorbing and reflecting heat from a nearby star, start to behave less like planets and more like stars. A true star generates heat through nuclear fusion, the smashing together of hydrogen atoms to release energy. That requires enormous mass and pressure, but the gravitational compression inside an object with 15 to 20 Jupiter masses creates pressure that approaches the lower boundary of fusion conditions. Scientists are genuinely uncertain whether any fusion processes are happening inside this object. At 15 Jupiter masses, most models say no. At 20 Jupiter masses, the probability increases sharply. And since the actual mass of this world has a range of uncertainty between those two numbers, the honest answer is that nobody knows for certain. A planet that might be fusing atoms in its core, a planet that glows with its own heat across hundreds of light years, a planet still feeding from a disk, still growing. And the challenge of figuring out exactly what it is comes down to a problem no telescope has been able to fully solve yet. The dust surrounding it hides the truth. Science loves clean categories. Planet, star, moon, galaxy, each label carries a set of rules, and those rules help scientists communicate clearly. When two astronomers use the word planet, they are supposed to mean the same thing. The system works well until the universe hands you something that refuses to fit neatly into any box. HD 100,546b is exactly that kind of object. The category that matters here is the brown dwarf. A brown dwarf is an object that formed with more mass than the largest planets, but with less mass than the smallest stars. It is massive enough that its core squeezes hydrogen together, but the pressure never quite reaches the level needed for sustained nuclear fusion. It glows faintly with the heat of that compression and whatever accretion it went through during formation, but it never truly ignites the way a star does. Over billions of years, it slowly cools and dims into darkness. The International Astronomical Union, the global body that sets the official definitions used in astronomy, puts the upper mass limit for a planet at 13 Jupiter masses. Anything above that, they classify as a brown dwarf, assuming it formed through certain processes. Here is the problem. This object sits between 15 and 20 Jupiter masses. That range of uncertainty matters enormously. If the true value is closer to 15, some models suggest it could still count as a planet formed inside a disk, rather than a collapsed cloud. If the true value is closer to 20, the brown dwarf classification becomes much harder to argue against. The situation gets even more complicated because formation method matters too. Two objects with the same mass can receive different classifications depending on how they formed. A world that built itself gradually from a rocky core surrounded by infalling gas is treated as a planet. An object that collapsed directly from a contracting pocket of gas in the same way a star does is treated as a brown dwarf. The current data does not clearly rule out either option for this world. Astronomers publishing on this object regularly describe it as sitting on the planetary and substellar boundary. That phrase is scientific language for, we genuinely do not know what this is. What makes the debate more than just academic is the implication for how common these objects are. If HD 100,546b is a planet, then massive planets can form much faster and at much larger sizes than current models predict. Every simulation of planetary formation would need revision. If it is a brown dwarf, then the story shifts toward understanding how failed stars end up embedded in planet-forming disks orbiting regular stars. That scenario raises its own chain of unsettling questions about what other massive, dim objects might be hiding in disks around young stars across the galaxy. Either answer rewrites something important. And right now, the main reason scientists cannot settle the debate is not the mass estimate. It is the wall of dust and gas surrounding the planet, blocking the clearest view. What hides behind that dust is even more complicated than the boundary debate suggests. Astronomy depends on light. Every measurement, every image, every calculation about a distant object starts with light reaching a detector. Telescopes collect it, sort it by wavelength, and translate it into data. The further an object is, the fainter the light becomes, and the more carefully scientists have to work to pull a signal out of the background noise. Now add a thick wall of dust between the telescope and the object you are trying to measure. The star that HD 100,546b orbits is a young, bright star surrounded by a protoplanetary disk. That disk is a massive flat sheet of gas and dust that extends hundreds of billions of miles outward from the star. It is the leftover construction material from the system's formation, and the planet sits embedded inside it. Visible light cannot penetrate dense dust. Try shining a flashlight through a thick blanket. Almost nothing gets through. The disk around this system acts like that blanket, except it stretches across enormous distances in every direction. Any telescope trying to take a direct image of the planet has to fight through this barrier. Scientists get around this problem by switching to infrared and submillimeter wavelengths. These types of light have longer waves that pass through dust more easily. Infrared telescopes like the James Webb Space Telescope were designed specifically to peer through dusty environments and see objects hidden inside them. But even with those tools, interpreting what you see is tricky. When telescopes image this region and pick up a glowing source near the planet's location, they cannot immediately confirm whether that glow is coming from the planet itself or from the surrounding disk material that the planet is disturbing. A planet with strong gravity carves a spiral pattern into its disk. The friction and compression at the edges of those spiral arms generates heat. That heat creates its own glow, and that glow overlaps with any glow coming directly from the planet. Some scientists who published on this system argued that the original size estimate of over 600,000 miles includes not just the planet, but the heated disk material clumped around it. If they are right, the planet's actual body could be meaningfully smaller, shifting its mass estimate and potentially changing its classification. Other scientists reviewed the same data and stood by the larger estimate. This is how the debate has sat for years. Two groups, same data, different interpretations. The James Webb Space Telescope has been observing young star systems with planet-forming disks as one of its primary science missions. The resolution it achieves is sharper than any previous infrared observatory. Scientists expect that continued observations will eventually cut through the ambiguity and reveal a clearer picture of what this object actually is. Until that data comes in, the situation remains genuinely open. An object with an uncertain mass, an uncertain size, an uncertain classification, and an uncertain formation story, hidden behind a curtain of dust 359 light-years away. Still feeding, still glowing, and every day it sits there, it is adding more mass from the disk around it, which means the debate about where it falls on the classification scale is a moving target. Something else entirely sits on the confirmed end of the scale, and it is so well understood, so clearly measured, that scientists know exactly how it will die. The universe has objects that almost became stars. They gathered enough mass during formation to compress their cores and heat their interiors. They glowed. They radiated. For a while, some of them even fused a form of hydrogen called deuterium, releasing brief bursts of nuclear energy, but the fusion could not sustain itself. The object never grew massive enough to ignite the main process that powers true stars. So it cooled, it dimmed. Over millions and billions of years, it faded toward darkness. These are brown dwarfs, and they are everywhere. Astronomers estimate there may be as many brown dwarfs in our galaxy as there are regular stars. They are hard to detect because they produce little visible light. They mostly radiate in infrared, the same wavelength range as heat from a warm body. For most of human history, we had no instruments sensitive enough to find them in large numbers. The first confirmed brown dwarf was only discovered in 1995, the same year that the first hot Jupiter exoplanet was found. Two discoveries in the same year that completely reshaped our picture of what the galaxy contains. Brown dwarfs range in mass from about 13 Jupiter masses at the low end up to roughly 80 Jupiter masses at the high end. Below 13 you have the most massive planets. Above 80 sustained fusion kicks in and you have a true star. Brown dwarfs occupy the entire middle space between those two boundaries. What makes them strange to study is that their behaviour overlaps with both planets and stars depending on their mass and age. A young brown dwarf near the upper mass limit looks and behaves somewhat like a very dim, very cool star. An old brown dwarf near the lower mass limit, after billions of years of cooling, can have atmospheric temperatures similar to a gas giant planet. Some even develop weather. Clouds of iron droplets and silicate dust form in their atmospheres. Storms rage across their surfaces for thousands of years. The classification of any object near these boundaries matters enormously for understanding the system it sits in. If HD 100,546b is a brown dwarf, then it is a failed star orbiting a young star, and the disk around that star is a planetary nursery being dominated by this massive dim companion. The implications for what other planets can form in that system change completely. Scientists use several tools to try and settle these boundary cases. Spectroscopy lets them analyse the chemical makeup of an object's atmosphere by studying which wavelengths of light it absorbs. Certain molecules appear at certain temperatures and pressures. By matching those molecular signatures to models, researchers can estimate temperature, composition, and sometimes mass with more precision than direct imaging allows. For the system containing the object we have been discussing, the dusty environment limits how well spectroscopy can work. The molecules in the disk itself contaminate the signal from the planet. Brown dwarfs close enough to image directly, without disk interference, have given scientists a much cleaner look at what happens when mass pushes right up against the boundary of stellar ignition. And the confirmed giant sitting in a clear, dust-free environment, known as P67b, gives scientists something even more striking. A world so thoroughly measured that every property is known, including the countdown to its destruction. Sometime around 2017, a planet got confirmed that made physicists genuinely reconsider what the word planet means. A team of astronomers studying data from ground-based observatories identified a transiting planet. Transiting means the planet passes in front of its host star from our line of sight. When it does, it blocks a small fraction of the star's light. By measuring exactly how much light gets blocked and for how long, scientists can calculate the planet's size with high precision. What they calculated stunned them. This world, now catalogued as P67b, has a radius more than twice that of Jupiter. Put another way, you could fit over 8 Jupiters inside it by volume. It is enormous. But enormous alone was not the part that broke the physics. Mass matters alongside size, and P67b has a mass of roughly 0.8 times Jupiter's mass. Think about that for a moment. A planet more than twice Jupiter's size, holding less mass than Jupiter itself. Take a ball twice the size of a basketball but lighter than a baseball. The physics of that should not work. And on most planets, it would not. But this world orbits its host star at a distance so close that one full orbit takes only 4.8 Earth days. Less than 5 days for an entire year. At that distance, the planet is being bathed in radiation at levels hundreds of times greater than what Earth receives from our own star. That radiation does something remarkable to the planet's gas. It pumps enormous amounts of energy into the outer atmosphere, heating the gas so intensely that it expands outward in every direction. The planet inflates like a balloon left in the sun. Its gases spread out over a volume far larger than Jupiter occupies, but the total mass stays the same. The result is a planet with a density lower than styrofoam. Some calculations put its average density lower than that of a marshmallow, an object twice the size of the largest planet in our solar system, and you could theoretically push a finger through its outer layers with less resistance than a sugary snack. Scientists call these objects hot Jupiters, specifically the inflated variety. They form a category of their own because standard models of gas giant formation do not produce them. Theorists have spent years trying to understand exactly which mechanisms drive the inflation, and the debate is still ongoing. Ohmic dissipation, tidal heating, and atmospheric circulation all get mentioned. No single explanation covers every case. P67b sits at the extreme inflated end of the spectrum. Its density is so low that it represents a test case for any proposed inflation mechanism. Whatever is puffing this planet up is working with extraordinary efficiency. And the process is still running. The planet is still being irradiated, its atmosphere is still expanding, and its host star is not staying stable. Something is happening to that star that will eventually make the inflation irrelevant. Because what comes next for this planet is complete obliteration, unfolding on a timeline that scientists have calculated down to the nearest 100 million years. Picture standing at a distance from a bonfire that gets so hot it starts to push your skin back. Now picture a planet doing the equivalent of standing inside that bonfire every single day for billions of years. P67b orbits its host star at a distance of roughly 2.5 million miles. That sounds large until you compare it to Earth's distance from our own star, which is about 93 million miles. This planet sits more than 35 times closer to its star than we sit to ours. At that range, the gravitational pull of the star is immense, which is why the orbital period, the time it takes to complete one full trip around the star, is only 4.8 Earth days. Planets closer to a massive object orbit faster. This is one of the most reliable laws in all of orbital mechanics, established by Johannes Kepler over 400 years ago. The relationship is precise and mathematical. P67b follows that law to the letter, which is exactly why its orbit period confirms just how dangerously close it sits. But the closeness does more than just set the orbital speed. It creates a phenomenon called tidal locking. When a planet orbits this close to a star, the star's gravity pulls harder on the side of the planet facing it than on the far side. That difference in pull stretches the planet slightly, and, over time, slows down the planet's rotation until one side permanently faces the star and the other side permanently faces away. The planet stops spinning relative to its star. One side of P67b exists in permanent daylight. The temperatures there reach levels that would vaporize most metals. The other side sits in permanent darkness, cold and shadowed, never seeing direct starlight. The boundary between these two zones is a permanent line running from pole to pole, where twilight is the only condition that ever exists. This temperature difference between the two hemispheres is extreme. Hot on one side, cold on the other, with no rotation to redistribute the heat evenly around the globe. The result is a powerful atmospheric engine. Heat rises on the day side, rushes toward the night side at supersonic speeds, cools down, and races back. The winds this process generates are continuous, relentless, and violent. Scientists have measured wind speeds on similar planets using spectroscopy. By analysing how the light from the star shifts as it passes through the planet's atmosphere at different points in the orbit, they can detect the motion of gases. The readings show winds moving at thousands of miles per hour, speeds that would reduce any structure known to engineering into fragments within seconds. P67b lives in this permanent storm. Day and night never change, winds never stop, and the star overhead never moves. The closeness that creates this situation also puts the planet in danger of something else entirely. At this distance, the star's outer atmosphere, the corona, extends far enough that the planet skims through the outermost edges of stellar material during each orbit, and the star is beginning to change in a way that will make that skimming far more dangerous. Radiation is not just light, it is energy travelling through space. Visible light is radiation. Ultraviolet light is radiation. X-rays are radiation. Each type carries a different amount of energy depending on its wavelength. Shorter wavelengths carry more energy. Longer wavelengths carry less. The star hosting P67b pumps out radiation across all of these wavelengths. The ultraviolet and X-ray portions are particularly powerful and particularly damaging to a planet sitting this close. When high-energy radiation strikes the upper atmosphere of a gas giant, it gets absorbed by the gas molecules there. Those molecules take in the energy and heat up. Heated gas expands. This is basic physics that you can test with a balloon. Warm a balloon and the gas inside it expands, pushing the rubber outward. The balloon grows. A planet's atmosphere works the same way, except there is no rubber balloon holding the gas in. The only thing keeping the atmosphere from drifting away is the planet's own gravity. And gravity has limits. As the atmosphere heats up and expands, the outer layers of gas get pushed further and further from the centre of the planet. The further they get from the centre, the weaker the planet's gravitational grip on them becomes. Gravity drops off with distance. At some point, the heated outer gas reaches a level where the planet's gravity can no longer hold it. At that point, the gas escapes, it drifts off into space and never comes back. This process is called photoevaporation. It is responsible for reshaping the atmospheres of thousands of planets across the galaxy. For most planets orbiting at safer distances, photoevaporation is slow and minor, a thin trickle of gas lost over billions of years. For P67b, at this extreme proximity, the process is aggressive. Scientists estimate the planet is losing a significant portion of its atmosphere continuously. The escaping gas does not just vanish quietly, it flows outward in a stream, forming a comet-like tail of material that trails behind the planet as it orbits. This tail has been detected observationally using a technique that measures helium absorption in the planet's atmosphere. Helium in the upper layers absorbs a specific type of infrared light. When scientists measured the light from the star as the planet passed in front of it, they detected far more helium absorption than the planet's body alone could account for. The excess absorption came from the tail. The tail extends for enormous distances, thousands of miles of escaping gas glowing faintly in infrared, marking the path the planet has already travelled in its orbit. What makes this process unstoppable is feedback. As the planet inflates, its outer atmosphere gets pushed even further from the centre, where the planet's gravity is even weaker, which means the radiation strips away even more gas. which means the remaining atmosphere expands further. The cycle reinforces itself. The planet is caught in a loop it cannot exit. And the source of that loop, the radiation bombarding it from the star above, is about to intensify in a way that will accelerate everything dramatically. Comets develop tails when they travel close to a star. Solar radiation and the flow of charged particles from the star push gas and dust away from the comet's surface, creating a glowing stream that always points away from the star regardless of which direction the comet is moving. That tail is beautiful. It is also a sign of loss. The comet is literally evaporating. Each pass near the star leaves it a little smaller. P67b is doing the same thing. Except it is a planet the size of 2 Jupiters, and it makes a full pass every 4.8 Earth days. The tail detected behind this planet is made primarily of helium. Helium is one of the 2 main ingredients in a gas giant alongside hydrogen. In the upper atmosphere of P67b, radiation from the star energizes helium atoms to a state called metastable triplet helium. In this state, those atoms absorb a very specific type of infrared light. This absorption signature is detectable by telescopes measuring the starlight passing through the planet's atmosphere. When scientists observed this planet transiting its star, they measured how much light the planet blocked at different wavelengths. At the wavelength that metastable helium absorbs, the planet blocked far more light than its physical disk alone could explain. The blocking started before the planet's edge crossed the star, and continued after the far edge had already cleared. That extended blocking came from the helium tail streaming behind the planet for thousands of miles. The detection was published and has since been used as a model for how to study atmospheric escape on other planets. P67b became a textbook case for what heavy radiation bombardment does to an unprotected gas giant atmosphere. But here is what makes the tail more than just a measurement curiosity. It is a direct window into the planet's future. The rate at which gas escapes determines how long the planet can maintain its current size. Scientists run calculations to estimate how many billions of years the planet has before the mass loss becomes severe enough to fundamentally change its nature. A planet losing its outer atmosphere continuously will eventually shrink below the runaway evaporation threshold, where the remaining denser atmosphere is held more tightly by gravity. At that point, the loss slows dramatically. In many cases, what you get at the end of that process is a small, dense, rocky or metallic core. The gas giant has been stripped down to its skeleton. These stripped cores, called Chthonian planets, represent what happens to hot Jupiters that survive long enough to lose all their gas. P67b may never reach that stage, because before the gradual evaporation can finish its work, something far more abrupt is scheduled to happen. The star above this planet has been quietly changing its internal structure for millions of years, and that change is now accelerating toward an event that will make the helium tail look minor. The star is swelling, and it is heading directly for the planet. Stars do not burn forever. Every star in the universe runs on fuel. Specifically, hydrogen in a star's core. Hydrogen atoms fuse together under enormous pressure and temperature to form helium, and that fusion releases the energy that makes the star shine. Our own star has been doing this for about 4.6 billion years. It has roughly another 5 billion years of hydrogen left. When the hydrogen in the core runs out, the star does not simply go dark. Instead, something more dramatic happens. The core contracts under its own gravity, while the outer layers of the star expand outward enormously, cooling as they spread. The star swells to hundreds of times its original size. Its surface temperature drops, shifting from the bright white yellow of a main sequence star to a deep, cooler red. Astronomers call this a red giant. The host star of P67b is already on this path. Scientists classify it as an evolved star, meaning it has exhausted a significant portion of its core hydrogen and is beginning the transition toward the red giant phase. The star is expanding. Its radius is already larger than a standard main sequence star of comparable mass would be. and the expansion has not stopped. Astronomers have run calculations on the system's future. The projections are precise within a range of a few 100 million years. They estimate that within 150 million to 500 million years, the expanding star will reach the orbital distance of the planet. At that point, the planet will be inside the star. The outer layers of a red giant are not solid or liquid. They are an extremely thin, extremely hot gas extending outward in every direction. For a planet orbiting inside this envelope, the experience is one of drag and incineration simultaneously. The planet moves through gas that resists its orbit, slowing it down. As the planet slows, its orbit decays, pulling it inward. Closer to the centre, the gas is denser and hotter. The drag increases. The orbit decays faster. The planet spirals inward toward the core. Meanwhile, the radiation intensity at the planet's location, already extreme at its current orbital distance, increases dramatically as the star expands around it. Temperatures climb past any point the planet's atmosphere can withstand. The outer layers of gas evaporate in a fraction of the time that steady photoevaporation would require. Scientists published updated models in 2025 that confirmed this fate for P67b. The timeline is set. The process is running. For perspective, 150 million years sounds impossibly far away, but the age of the dinosaurs on Earth ended about 66 million years ago. 150 million years is roughly 2.5 times that entire span of prehistory. The universe operates on scales that make human history feel like a single breath. P67b will be gone on a timescale that is distant but not infinite, and its destruction will come from inside the very system that created it. But another world on the opposite extreme, orbiting at a distance so vast that the concept of a year becomes almost meaningless, tells a completely different story about how giant planets can exist. A red giant does not arrive suddenly. The transformation from stable main sequence star to swollen giant takes millions of years. From the perspective of any observer far away in the galaxy, it looks like a slow brightening and reddening of a point of light in the sky. From the perspective of a planet sitting in the path of the expanding outer edge, it is a relentless, unstoppable tide moving outward at a rate too slow to notice in a human lifetime, but too fast to escape across astronomical time. For P67b, the sequence of destruction unfolds in stages. The first stage is already happening. Increasing luminosity from the evolving star means more radiation reaching the planet per second. More radiation means faster photoevaporation of the atmosphere. The helium tail already detected behind the planet grows longer and denser as the energy input rises. Gas loss that might have taken 1 billion years to cause significant damage gets compressed into a shorter window. The second stage begins when the star's outer layers expand far enough that the planet's orbital path sits inside the stellar atmosphere. At this point, the planet is not in space anymore, it is inside a star. The gas surrounding it on all sides exerts aerodynamic drag on the moving planet. Every orbit the planet completes burns a tiny bit of orbital energy into the surrounding gas. The orbit tightens. Astronomers have a precise term for this process. It is called common envelope evolution when it occurs in binary star systems, and orbital decay by stellar drag when it applies to a planet inside an expanding star. Either way, the result is inward migration toward the stellar core. The third stage is total ablation. As the planet spirals inward through increasingly dense and hot stellar material, its outer atmosphere strips away exponentially faster. Layers of gas that took millions of years to accumulate during the planet's formation peel off within thousands of years. The heating rate at the surface of whatever remains accelerates. Models suggest the planet's outer envelope of gas will be completely removed before it reaches the stellar core. What survives, if anything does, is the densest innermost region of the planet. For gas giants, the core is where pressures are extreme enough that hydrogen behaves as a metallic liquid and heavier elements like rock and metal sink toward the centre. This dense core, possibly about the size of Earth or Neptune, might briefly survive the journey inward. But eventually the temperature and pressure of the red giant interior overcome even that remnant. The materials dissolve into the stellar plasma and become part of the star itself. The planet that was once a world larger than 2 Jupiters, with a comet-like helium tail and supersonic storms, ends as a contribution to the mass of a swollen star, the atoms that made it scatter into stellar material indistinguishable from the rest of the fusion products accumulating in the dying giant above. Scientists can predict this future because the physics governing it is well understood. The calculation published in 2025 placed the destruction between 150 million and 500 million years from now. That range is large, but the destination is not in question. Somewhere in the galaxy, a world with the opposite problem from closeness exists, a planet so far from its star that understanding how it formed at all requires dismantling everything we thought we knew about planet formation. 460 light-years from Earth, in a region of the galaxy called the Rho Ophiuchi star-forming cloud, there is a planet doing something that should be impossible. It is orbiting its star at a distance of roughly 150 times the distance between Earth and our own star. To put that into miles, the gap between this planet and its star is approximately 14.5 billion miles. The star that Neptune, the farthest confirmed planet in our solar system, orbits sits at about 2.8 billion miles from our star. This planet's distance from its star is 5 times greater than Neptune's distance from ours. At that range, completing one full orbit takes an immense amount of time. Scientists calculate that 1 year on this world lasts approximately 1,900 Earth years. If a civilization had started tracking this planet's calendar at the time the ancient Roman Empire rose to power, it would still be in the middle of year 1 today. The planet is called Aurochs 42b. It has a mass 9 times greater than Jupiter and a radius 2.5 times larger. Those are numbers that qualify it firmly as a massive gas giant with no ambiguity about its classification. The mass is high but sits within the planetary range, comfortably below the brown dwarf threshold. What makes it scientifically explosive is its location. Every accepted theory of planet formation had, until this discovery, predicted that planets form close to their stars where the disk of material is dense enough. Farther out, the disk thins dramatically. The material gets sparse. The odds of enough matter clumping together to form a massive gas giant drop towards 0. Standard formation models gave essentially no probability to a planet the size of Aurochs 42b existing where it does. And yet, it exists. Scientists have verified the detection multiple times using direct imaging, meaning they can actually see this planet in telescope images rather than inferring it from wobbles or light dips. The Keck Observatory in Hawaii first confirmed it in 2013. Multiple follow-up observations from other facilities corroborated the finding. The planet is real. The distance is real. The mass estimate is as solid as the data allows. The confirmation raised an immediate question that nobody could answer cleanly. How did a planet 9 times the mass of Jupiter end up this far from its star? 2 main ideas emerged. The first is that it formed further inward, where the disk material was dense enough, and then migrated outward over time through gravitational interactions with other massive objects in the system. The second is that it formed directly from the collapse of a dense pocket of gas in the outer disk, the same way a star forms but at a smaller scale. Each explanation has problems. Outward migration to this distance requires a chain of gravitational interactions that is statistically unlikely. Direct collapse at the planetary mass scale in an outer disk contradicts observations of how outer disk material is distributed. Neither answer is clean. And the fact that it orbits a pair of stars rather than a single star adds another variable that complicates every calculation. Planet formation theory is built on a simple starting point. A star forms first. Around the young star, the leftover gas and dust from its birth flattens into a spinning disk. That disk is where planets grow. Material in the disk collides, clumps, and gradually builds up. Small grains become pebbles. Pebbles become boulders. Boulders become planetesimals. Planetesimals smash into each other and merge into planet cores. Cores with enough mass pull in surrounding gas and become gas giants. This model, called core accretion, has successfully explained the formation of planets in our solar system and many others. It makes specific predictions about where in a disk different types of planets form. Rocky planets form close to the star where it is too hot for ice to exist. Gas giants form beyond the snowline, a boundary where temperatures drop low enough for water and other molecules to freeze, providing extra solid material for cores to grow faster. In our solar system, the snowline sits at about 2.5 times Earth's orbital distance from our star. Jupiter formed just beyond it. Saturn formed further out. Uranus and Neptune formed even further still, though models suggest they may have migrated somewhat from their original positions. The outer edge of where core accretion can produce gas giants in reasonable timescales sits at roughly 30 to 50 times Earth's orbital distance. Beyond that, the disk is too thin, collisions are too rare, and a giant planet core cannot build up before the disk dissipates. Rox's 42BB orbits at 150 times Earth's orbital distance. That is, 2 to 5 times beyond the theoretical maximum. At 150 times out, the disk material density in the Rho-Ophiuchi cloud during this system's formation period would have been far too sparse for core accretion to work within any reasonable time frame. Scientists ran the numbers. The core accretion pathway takes millions of years even in favourable conditions. At 150 astronomical units, the growth timescale stretches to hundreds of millions of years, far beyond the lifespan of the disk itself. So core accretion is essentially ruled out. The alternative, disk instability, proposes that a sufficiently massive and cold disk can fragment directly under its own gravity. Rather than slowly building up from small pieces, a large chunk of disk material collapses all at once into a dense blob that contracts into a planet-sized object. Disk instability works faster, potentially in thousands of years rather than millions. But disk instability also has a size problem at this location. The masses required for a disk to become gravitationally unstable enough to fragment generally produce objects in the brown dwarf range, above 13 Jupiter masses, rather than planet-sized objects like the 9 Jupiter mass world that Rox's 42BB actually is. So neither major theory produces a clean prediction for a 9 Jupiter mass planet at 150 astronomical units. Some researchers have proposed that the system's binary star configuration, the fact that 2 stars are present rather than 1, may have played a role by distorting the disk in ways that promoted early fragmentation at specific locations. Others suggest that a third formation pathway, involving scattering from an inner disk that was denser than average, could explain the position. Every proposed solution to the puzzle adds complexity. And then there is the sky directly above this planet, which adds a feature no planet in our solar system has ever had to contend with. Most star systems are not single stars. Our star is unusual in that it orbits alone, without a stellar companion. Astronomers estimate that roughly half of all star systems in the galaxy contain 2 or more stars bound together by gravity. These binary and multiple star systems come in enormous variety. Some pairs orbit each other at distances comparable to the distance between Earth and our star. Others are separated by hundreds of times that gap. Each configuration creates a completely different environment for any planets that form nearby. Rox's 42b orbits a pair of young stars. The 2 stars in the system are gravitationally bound to each other, meaning they circle around their shared centre of mass continuously. The planet, at its extreme distance of 150 times Earth's orbital distance, orbits around the centre of mass of the entire binary pair rather than around one star individually. From the planet's perspective, what it orbits is a combined gravitational source made of 2 stars. The visual consequence of this for the planet's sky is remarkable. On Earth, we have one star in the sky. It rises, crosses the sky arc, and sets. On Rorox's 42b, there are 2 stars. Depending on the current separation between the stellar pair and the planet's position in its enormous orbit, these 2 stars could appear as distinct points of light or as a closely spaced pair. Unlike science fiction depictions of twin suns, they would not necessarily be equally bright or the same colour. Stars of different masses emit light at different temperatures, giving them distinct colours ranging from hot blue-white to cooler orange-red. The gravitational environment created by 2 stars is significantly more complex than one created by a single star. 2 gravitational sources create what mathematicians call a 3-body problem when combined with the planet. The 3-body problem has no clean, general solution. The motion of 3 objects interacting gravitationally over long periods is chaotic in a mathematical sense, meaning small changes in initial conditions lead to drastically different long-term outcomes. For RX's 42b's orbit to remain stable over billions of years, the geometry of the system has to fall within specific ranges. If the binary pair orbits each other closely enough, the planet's distant orbit can remain relatively stable. Researchers have assessed the system's stability and determined that the current configuration allows for a long-term stable orbit, but the margin is narrower than in single-star systems. The fact that the system hosts young stars also means the stars themselves are still settling. Young stars flare more frequently and intensely than mature ones. They release powerful bursts of radiation in events called stellar flares. With 2 young stars in the system, the planet faces flare events from 2 sources. These bursts of energy hit the planet's upper atmosphere and contribute to whatever atmospheric processes are occurring at this extreme distance from the stars. Even at 150 times Earth's orbital distance, the combined radiation from 2 young stars delivers meaningful energy to the planet. The atmosphere, largely unexplored, sits in a radiation environment quite different from any planet in our solar system. Everything about this system, from the impossible distance to the binary stars to the mystery of its formation, makes Rox's 42b one of the most scientifically challenging objects in modern planetary astronomy. And understanding how any planet gets detected at such distances requires a look at the remarkable toolkit scientists have built to find worlds they cannot directly touch. Finding a planet orbiting another star is one of the hardest things science has ever attempted. Stars are bright. Planets are dim. The light a planet reflects from its star is roughly 1 billion times fainter than the star itself. Trying to see a planet next to its star from Earth is like trying to spot a firefly hovering next to a lighthouse from 20 miles away. The lighthouse drowns everything out. So astronomers developed methods that sidestep the problem entirely. The most productive method ever used is called the transit method. When a planet passes in front of its host star from our line of sight, it blocks a small fraction of the star's light. The star dims slightly, then brightens again once the planet moves past. By measuring that dip precisely, scientists can calculate the planet's size. A larger planet blocks more light, a smaller planet blocks less. The timing of repeated dips reveals the orbital period. The depth of each dip reveals the planet's diameter relative to the star. This method works extraordinarily well for planets orbiting close to their stars, because those planets transit more frequently and block more light relative to their orbital position. P67b was confirmed this way. Its transits are measurable from ground-based telescopes because the planet is so large that even at 1% light blocking, the signal is unmistakable. The second major method is radial velocity, sometimes called the Doppler wobble. A planet does not orbit a star while the star sits perfectly still. Both objects orbit their shared centre of mass. For a massive planet, the star wobbles slightly. As the star wobbles toward Earth, its light shifts slightly toward the blue end of the spectrum. As it wobbles away, the light shifts toward the red. By measuring this shift with high-precision spectrographs, scientists can calculate the minimum mass of the planet causing the wobble. The first confirmed exoplanet around a main sequence star, found in 1995, was detected using this method. A third method is direct imaging. This is exactly what it sounds like, actually photographing the planet. It is the hardest approach and only works for planets that are very large, very bright in infrared light, and very far from their host stars. Farther from the star means less glare to compete with. ROX's 42BB was found this way. Its enormous distance from its host stars, combined with its size and infrared brightness as a young planet still radiating formation heat, made it detectable against the stellar glare using specialized optics that block out the central starlight. A fourth approach is gravitational microlensing. When a star with a planet passes in front of a more distant background star, the gravity of the foreground star bends and magnifies the background light. If a planet is present, it causes a brief secondary spike in that magnification. This method detects planets regardless of how far they sit from their star, but each event is unique and unrepeatable. Every method has blind spots. Transits only work when orbital geometry aligns perfectly with Earth's line of sight. Radial velocity struggles with low-mass planets and face-on orbits. Direct imaging needs the planet to be bright and far out. Microlensing gives one shot per event. Scientists combine all of these approaches across thousands of star systems to build a complete picture. And the picture they are assembling reveals that the universe is filled with worlds far stranger than anything in our own backyard. Strange enough that the weather alone on some of these planets is enough to make the detection methods feel almost boring by comparison. On Earth, the strongest winds ever recorded reached about 250 miles per hour during tropical cyclones. Those winds destroyed buildings, uprooted trees, and reshaped coastlines. They were considered among the most powerful natural forces humans regularly encounter on this planet. On hot Jupiters like P67b, winds routinely exceed 5,000 miles per hour. That speed is not a peak. It is sustained. Continuous. The atmospheric circulation on a tidally locked hot Jupiter runs like an engine that never powers down. The day side of the planet receives constant intense radiation from the nearby star. The gas there heats to extreme temperatures and rises upward. That rising gas has to go somewhere, so it flows toward the night side of the planet at the upper atmosphere level, dumping heat as it goes. Cooler gas from the night side flows back toward the day side at lower altitudes to replace it. This circulation pattern is a global heat engine. It runs because the temperature difference between the two hemispheres is so large that the gas cannot stay still. The scale of the planet ensures that this circulation covers thousands of miles in every direction, and the continuous energy input from the star keeps driving it without interruption. The result is wind speeds that pass through the sound barrier and keep going. On Earth, the speed of sound in air is about 760 miles per hour. Hot Jupiter winds exceed that by factors of 5 or more. These are supersonic atmospheric rivers wrapping around entire planets. The storms these winds create are unlike anything in our solar system. Jupiter's Great Red Spot, a storm system larger than the Earth that has lasted at least 350 years, would be considered a minor weather feature on a hot Jupiter. Storms on these worlds have nothing to stop them. On Earth, storms lose energy when they hit land or cold ocean water. On a gas giant with no solid surface, nothing interrupts the circulation. A storm can rage for thousands of years, growing and evolving, absorbing other storm systems, building into a permanent fixture of the atmosphere. Wind speed data from hot Jupiters has been gathered using a technique called phase curve analysis. As a planet orbits its star, the portion of its dayside visible from Earth changes. The brightness of the system changes in a predictable way with the orbital phase. By mapping exactly where the brightest point of the planet sits relative to the substellar point, the spot directly beneath the star, scientists can infer how far the hottest gas has been carried around the planet by wind. On many hot Jupiters, the hottest point sits significantly east of the substellar point. The winds have blown the heat hundreds of miles around the planet before it can radiate away. The faster the winds, the further east the hotspot sits. The measurement gives scientists a direct window into the speed and structure of an atmosphere they can never visit. And the material those winds carry is the most unexpected detail of all, because the clouds on these worlds are made of something that has absolutely no equivalent in Earth's weather. Earth has water clouds. Water evaporates from the oceans, rises into the atmosphere, cools at altitude, and condenses back into liquid droplets that form clouds. Those droplets fall as rain. The process is continuous and shapes life on the entire planet. Hot Jupiters have silicate clouds. Silicates are the same class of minerals that make up most of Earth's rock and sand. Quartz is a silicate. Glass is made from silicates. On Earth, silicates only melt at temperatures above about 3,000 degrees Fahrenheit, which is why rocks do not turn into clouds in normal conditions on our planet. On the day side of a hot Jupiter, temperatures regularly exceed 3,000 degrees Fahrenheit. At those temperatures, silicate rock would not just melt, it would vaporize. The rock turns into a gas, rises with the atmospheric circulation, and gets carried by the massive winds toward the cooler night side of the planet. On the night side, temperatures drop, still thousands of degrees by Earth standards, but significantly cooler than the day side. At these slightly lower temperatures, silicate vapor condenses. Just like water vapor condenses into liquid droplets on Earth to form rain clouds, silicate vapor condenses into tiny solid particles of glass on the night side of a hot Jupiter. These glass particles form clouds in the upper atmosphere. Then they fall. The result is rain made of glass. Tiny shards of silicate material, some liquid, some solid depending on altitude and temperature, falling downward through the thick atmosphere. The winds blowing at 5,000 miles per hour carry these particles sideways as they fall, creating horizontal storms of glass moving at supersonic speeds. For any hypothetical object caught in that atmosphere, the experience would be instantaneous destruction. The abrasion alone from glass particles moving at those speeds would reduce any known material to powder in seconds. Astronomers detected silicate clouds on exoplanets using a specific infrared observation technique. Different molecules absorb and emit light at specific wavelengths like a fingerprint. Silicon dioxide, the compound that forms glass, has a detectable signature in mid-infrared light. The James Webb Space Telescope has measured silicate cloud signatures in the atmospheres of multiple hot Jupiters, confirming that this form of weather is common across this class of planet. What varies between different worlds is the size of the silicate particles. On some planets, the particles are tiny grains like fine sand. On others, the particles clump into larger droplets before falling. The difference affects how the clouds look and how much light they reflect. Clouds of fine silicate grains scatter light very efficiently and make the planet appear bright. Clouds of larger particles absorb more light and make the planet appear darker. By studying how bright different hot Jupiters appear at different wavelengths, scientists can figure out which type of silicate clouds dominate their atmosphere. These measurements tell researchers about the temperature and pressure structure of the atmosphere at cloud level. Each new measurement reveals a little more about how alien these worlds truly are. And the violence of this weather has consequences for one aspect of hot Jupiter systems that many people assume would exist, but simply cannot. Every giant planet in our solar system has moons. Every single one. Jupiter has 95 confirmed moons. Saturn has over 140. Even Uranus and Neptune host extensive moon systems. Rings, like Saturn's iconic system, exist around all four of our gas giants. The presence of moons and rings around giant planets feels almost like a rule. For hot Jupiters, the rule breaks completely. The reason comes down to a concept called the Roche limit. Every planet has a gravitational influence zone around it, but that zone has a boundary. Closer than a certain distance from a massive planet, another object's own gravity is overwhelmed by the tidal forces of the larger body. The tidal forces pull harder on the near side of the small object than on the far side, stretching it apart faster than its own gravity can hold it together. The object disintegrates. That boundary is the Roche limit. For Jupiter, the Roche limit sits at about 110,000 miles from the centre of the planet. Any solid object smaller than a large moon trying to orbit inside that distance gets shredded into particles. Those particles spread into a ring rather than clumping into a stable moon. Saturn's rings exist because material inside Saturn's Roche limit cannot assemble into a moon. Hot Jupiters also have Roche limits. The problem is that their host stars have Roche limits too, and the hot Jupiter is already sitting extremely close to its star. The stellar Roche limit for a hot Jupiter's orbit means that the planet itself is already inside or very close to the region where the star's tidal forces become significant. For moons to orbit the planet, they would need to do so within the planet's own gravitational sphere of influence, called the Hill sphere. But the Hill sphere of a hot Jupiter gets severely compressed by the nearby star's gravity. The math works out badly for moons. The compressed Hill sphere of a hot Jupiter sits at just a few planetary radii. Moons trying to orbit within that narrow zone face powerful tidal forces from both the planet and the star simultaneously. Over time, those forces push the moon's orbit toward instability. The moon either spirals inward and crashes into the planet, or gets ejected outward by the star's gravitational perturbations. Scientists have modelled the moon stability timescales for various hot Jupiter configurations. The conclusion across most models is the same. Any moon around a hot Jupiter loses orbital stability on timescales of millions to hundreds of millions of years. In the 4 billion year plus age of most planetary systems, any moons that ever formed around hot Jupiters have long since been removed. Rings face the same fate even faster. The particles that make up a ring system are even more sensitive to tidal perturbations than solid moons. Ring systems around hot Jupiters dissipate rapidly by cosmic standards. The sky above a hot Jupiter is a stripped-down environment, no moons crossing overhead, no rings arcing across the atmosphere. Just the enormous, swollen star filling a large portion of the sky, pouring radiation downward continuously. That gravity stripping away moons is the same gravity doing something else entirely to the atmosphere. Something that reveals exactly how close these planets come to tearing apart at the molecular level. Gravity is invisible. It has no smell, no sound, no colour, but it shapes everything in the universe. On Earth, gravity pulls you downward at a rate that gives you a certain weight. Stand on Jupiter, and the gravity at the cloud tops is roughly 2.5 times stronger than Earth's. You would weigh 2.5 times what you weigh now. Your legs would struggle to hold you. Walking would feel like moving through thick mud. Now scale up to a world with 9 or 15 or 20 times Jupiter's mass. Surface gravity, meaning the gravitational pull at the outer visible layer of a gas giant, scales with mass divided by radius squared. A planet 20 times more massive than Jupiter, but only a few times larger in radius, would have a surface gravity several times stronger than Jupiter's. We are talking about a gravitational pull at the cloud layer, roughly 5 to 6 times what Jupiter produces, and around 15 times what Earth produces. Any spacecraft approaching such a world would need extraordinary shielding and structural strength just to survive the tidal gradient, the difference in gravitational pull between the near side and far side of the craft. As the spacecraft descended through the atmosphere, the drag would increase rapidly. The dense gas would resist movement with enormous friction. Heat generated by that friction would challenge any thermal protection system designed today. But the more immediate problem for any approaching object is the radiation environment around hot Jupiters specifically. The strong magnetic fields that massive gas giants generate create trapped radiation belts around the planet. Jupiter's radiation belts are already intense enough that the Juno spacecraft, a probe built to study Jupiter, was designed to make fast passes through the radiation zone rather than sustained orbits within it. Around a hot Jupiter receiving thousands of times more stellar radiation than Jupiter receives, the radiation environment is orders of magnitude more hostile. Charged particles stripped from the planet's atmosphere by stellar radiation form an extended plasma cloud around the planet. Any spacecraft flying through this region would be bombarded by high-energy particles at rates that would damage electronics and irradiate crew members to lethal doses within hours. Getting close to these worlds with current technology is essentially impossible. Scientists study them entirely from a distance, using light as their only tool. Even the gravitational tidal forces from a planet like P67b would affect nearby objects meaningfully. At the distance of a potential moon orbit, the tidal stretch on a spacecraft would be measurable by sensitive instruments. Closer in, toward where the planet's dense inner atmosphere begins, the tidal forces become strong enough to distort the shape of the spacecraft itself. For HD 100,546b, the forming giant, the situation is even more extreme. The active accretion process surrounding it means any approaching object would collide with infalling material long before reaching the planet. Streams of gas and dust moving at high velocity toward the planet would impact anything in their path. These worlds are not just scientifically extreme, they are physically unreachable with any technology humanity possesses today. And the chemistry happening in their atmospheres under extreme radiation conditions produces results that no laboratory on Earth can fully replicate. X-rays carry enough energy to knock electrons off atoms. On Earth, hospitals use X-ray machines at very low doses to image bones through skin. Those brief exposures are carefully controlled because even short X-ray doses accumulate damage in biological tissue. Lead vests protect the parts of the body not being imaged. Long-term X-ray exposure causes cell damage, mutation, and eventually cancer. Now imagine a planet receiving constant X-ray bombardment from a nearby star every second for billions of years. The upper atmosphere of a hot Jupiter sits directly in the path of this radiation. Ultraviolet light and X rays from the host star stream into the planet's outer atmosphere and immediately begin breaking apart molecules. Ultraviolet photons carry enough energy to break the chemical bonds that hold hydrogen molecules together. The two hydrogen atoms in each molecule separate. X-rays go further, stripping electrons entirely from atoms and turning them into ions, electrically charged particles. This ionization process creates a layer in the planet's upper atmosphere called the thermosphere. In this layer, the gas is so energized that it behaves differently from the gas lower down. The ionized atoms and free electrons interact with the planet's magnetic field, creating complex electrical currents in the atmosphere. These currents generate additional heat through a process called ohmic heating, where electrical resistance in the conducting gas converts electrical energy into thermal energy. For P67b, scientists believe ohmic heating may be one of the main contributors to the planet's extreme inflation. The electrical currents running through the ionized upper atmosphere deposit extra heat into the planet's interior, driving the outer layers to expand even further than the direct radiation heating alone would cause. The long-term chemical effects of sustained X-ray bombardment are profound. Elements that would normally form stable molecules in a cooler atmosphere get broken apart repeatedly. Carbon-based molecules that form in the lower atmosphere rise, get destroyed by radiation in the upper layers, and their component atoms fall back down. The cycling of these atoms through repeated destruction and reformation drives a constant chemical churn in the atmosphere. Certain molecules become enriched, others get depleted over time. Carbon monoxide and carbon dioxide behave differently under X-ray bombardment than they do in calmer conditions. Water molecules get dissociated into hydrogen and oxygen, with the lighter hydrogen often escaping to space while the heavier oxygen remains. Over millions of years, this preferential loss of hydrogen alters the ratio of elements in the atmosphere. Scientists use spectroscopy to read these chemical fingerprints. The specific mix of molecules in a planet's atmosphere tells a story about the radiation history of that world. Two planets of identical initial composition but different radiation histories will develop different atmospheric chemistry over time. For the most extreme X-ray environments around the youngest and most active stars, the atmospheric destruction can be severe enough that gas giant planets lose their entire hydrogen and helium envelopes within a few 100 million years, leaving only the dense rock and metal core behind. The radiation does not just change a planet's chemistry, it changes what a planet fundamentally is. And that destructive power works not just on individual planets, but on entire solar systems during the formation process. A forming giant planet is the most selfish object in a young solar system. During the early stages of a solar system's life, the central star is surrounded by a disk of gas and dust. This disk is the raw material for every planet, moon, comet, and asteroid that will ever exist in that system. The material is finite. Whatever gets used to build one object is unavailable for building anything else. When a giant planet core reaches a critical mass, roughly 10 times Earth's mass, something changes. The core becomes massive enough that its gravity can pull in gas from the surrounding disk directly, not just solid particles. This process is called runaway gas accretion, and it proceeds rapidly. Once triggered, it is largely unstoppable. The forming giant does not just pull in the gas immediately surrounding it. Its gravity reaches outward and disturbs the disk across enormous distances. A process called gap opening occurs. As the planet grows, it pulls material from both the inner and outer edges of its orbital path. This creates a cleared region in the disk called a gap, a ring of lower density material centered on the planet's orbit. The clearing of this gap has consequences for everything else forming in the system. Material that would have drifted inward to potentially build rocky planets in the inner system now gets intercepted by the giant planet's gravity. Some of this material falls onto the growing giant, some gets flung into highly elliptical orbits, some gets ejected from the system entirely. The disk inside the giant planet's orbit gets starved of the raw material it needs to build inner rocky planets. If the giant forms early enough and grows fast enough, it can prevent the formation of any inner rocky planets at all. The disk outside the giant's orbit gets similarly disrupted, with material piling up at the outer edge of the gap or getting flung into distant, unstable orbits. Astronomers have observed this gap opening process directly in several young star systems using the Atacama Large Millimeter Array, a radio telescope array in Chile that images the thermal emission from dust in planetary disks. Images from this observatory show gaps, rings, and spiral arms in young disks, with the spiral arms being particularly significant. They are the gravitational wake of a forming giant planet, a visible signature of the planet's influence on the surrounding material. HD 100,546b is almost certainly doing this right now. Sitting embedded in its host star's disk, it is actively carving its environment. The spirals in that disk observed by telescopes are the fingerprint of this enormous forming object reshaping everything around it. The material it pulls in goes toward its own mass. The material it scatters goes into chaotic orbits or out of the system entirely. Whatever smaller, rocky worlds might have formed in that system, their chances of survival near this forming giant are minimal. The violence of giant planet formation is written into disk structures across the galaxy, and the downstream consequences for the inner regions of affected solar systems tell a darker story about how most planetary systems actually end up. The star hosting HD 100,546b is a bright young star roughly 2.4 times the mass of our own star. Around it spins a disk that extends outward for enormous distances. Inside that disk, multiple gaps and ring structures have been imaged by telescopes. Astronomers studying those structures have identified at least 2 separate gap regions in the disk, one of which is associated with the giant planet we have been discussing. The second gap, located at a different orbital distance, suggests that another forming object may exist or have existed at a separate location in the disk. The presence of multiple gaps in a disk is significant. Each gap requires a gravitational source massive enough to clear the surrounding material. Either multiple forming planets created each gap, or a single massive object in an unusual orbit swept through different regions at different times. For this system, the leading interpretation is that the disk contains at least one additional forming planet inside the orbit of the large outer giant. Some researchers have proposed that a second smaller planet candidate may be forming closer to the star, creating the inner gap structure seen in disk images. Here is where the disruption story gets serious. The outer giant, with 15 to 20 Jupiter masses of gravitational influence, does not sit politely in its own lane. Its gravity reaches inward across the disk, with enough force to destabilize material at other orbital distances. Smaller forming objects inside its orbit face gravitational perturbations that can shift their orbits, trigger collisions with other forming bodies, or cause them to spiral inward or outward from their original positions. Simulations of young planetary systems with a massive outer giant consistently show that the giant shapes or destroys what forms in the inner disk. If a second planet candidate in this system was building itself up from the inner disk material at the same time the outer giant was clearing its own region, the gravitational competition between them would have been fierce. The outcome depends on timing and mass ratios. If the outer giant reached significant mass before the inner planet built up substantial size, the inner planet's orbital stability would be compromised early. Perturbations would cause its eccentricity, how elliptical its orbit is, to increase. A more eccentric orbit leads to faster relative speeds during disk interactions, which changes accretion rates and can trigger destructive collisions rather than constructive mergers. Scientists cannot yet observe any confirmed inner planet in this system with certainty. The dusty disk that makes the outer giant hard to measure precisely also obscures the inner regions where a smaller forming planet would exist. The signal from a smaller, dimmer object buried in a bright disk is even harder to extract. What the disk structure itself suggests, through the gaps and ring features that are observable, is that multiple gravitational actors have been reshaping this disk simultaneously. The giant outer object dominates, but the architecture around it carries the signatures of a chaotic and contested early history. Every disk gap is a scar left by a forming planet. Some of those scars represent survivors. Others may represent planets that formed, were disrupted, and either crashed into the star or were flung into interstellar space. Understanding this violence in forming systems required scientists to first confront a discovery in the 1990s that shattered every model they had built. Before 1995, planetary science had a settled story. Planets formed in their place and stayed there. Rocky planets close to the star, gas giants far out where the disk was cold enough. Each planet formed in the region where the local conditions matched what it needed to build up. The solar system was the template. Every textbook assumed other systems would look broadly similar. The planet found orbiting 51 Pegasi in 1995 destroyed that framework in a single discovery. A gas giant half the mass of Jupiter, orbiting at a distance so close to its star that 1 year lasted 4 days. The temperature at the planet's cloud tops exceeded 2,000 degrees Fahrenheit. The star's tidal forces were powerful enough to lock the planet's rotation permanently. Everything about its location violated the existing formation models. Astronomers had 2 options. They could question whether the detection was real, or they could accept the detection and question everything they believed about planet formation. Multiple independent observations confirmed the planet within months. The detection was real. The existing models were wrong. A scramble to explain hot Jupiters produced a theory that, once scientists accepted it, turned out to have even more dramatic implications than the planets themselves. The theory was planetary migration. Giant planets do not have to stay where they form. Under the right conditions, they can move. They can travel inward, across the entire inner region of a solar system, ending up parked close to their star. The migration mechanism involves the forming giant interacting gravitationally with the disk of material around it. As the planet orbits, it pushes on the gas in the disk ahead of it and pulls on the gas behind it. This interaction transfers orbital energy between the planet and the disk. Under certain conditions, the planet loses orbital energy to the outer disk and gains from the inner disk at an unequal rate, causing a net loss of orbital energy overall. The planet spirals inward. This process, called Type 2 migration, can move a giant planet from a formation location several times Earth's orbital distance all the way inward to within a few hundredths of Earth's orbital distance, essentially on top of the star. The migration happens over timescales of hundreds of thousands to millions of years, fast by planetary standards. The implications of migration went far beyond explaining hot Jupiters. If giant planets could migrate inward, they would destroy anything in their path. Rocky planets that had been quietly building in the inner disk would face the gravitational force of a migrating giant sweeping through their region. They would be flung out of the system, shattered in collisions with each other, or absorbed by the star. Systems that hosted inward migrating giants ended up with cleared inner regions and a hot Jupiter parked close to the star. The inner rocky planet population, the region where water-bearing, potentially habitable worlds might exist, was wiped out. Our solar system does not have a hot Jupiter. Jupiter stayed at its current orbital distance. That fact now looks less like the normal outcome, and more like an unusual result of specific conditions during our solar system's formation. The presence of Saturn may have stabilized Jupiter's migration, preventing it from moving inward. We got lucky. Most systems apparently do not. Migration is not subtle. When a giant planet begins moving inward through a planetary disk, it acts like a wrecking ball swinging through a construction site. Everything in its path either gets absorbed into the giant, flung to a distant orbit, or ejected from the system entirely. The inner disk, which had been patiently accumulating the building blocks for rocky planets, gets disrupted in a span of time that is short by cosmic standards. The wrecking progresses in stages. The migrating giant first reaches the outer edge of the inner rocky planet formation zone. Its gravitational influence starts affecting forming bodies there. Planetesimals, objects ranging in size from a few miles to a few hundred miles across, get perturbed out of their nearly circular orbits into elliptical ones. Objects on elliptical orbits cross the paths of other objects at higher relative speeds. Collisions that would have built larger bodies instead shatter them into smaller fragments. As the giant moves deeper into the inner system, the gravitational perturbations intensify. Larger protoplanets, objects that had grown to the size of the Moon or Mars after millions of years of collisions, get their orbits destabilized. Some get captured in resonance with the migrating giant, meaning the ratio of their orbital period to the giant's orbital period locks into a simple fraction like 2:1 or 3:2. These resonances amplify perturbations over time, gradually pushing the trapped planet into a more and more extreme orbit. The end states vary. Some inner planets get flung directly into the star. Others get ejected from the system on hyperbolic trajectories, never to return. Some get absorbed by the migrating giant itself during close approaches. The migration eventually stops. Stopping mechanisms include the disk running out of material to continue driving the migration, the disk dissipating entirely as the star's radiation clears it away, or the planet reaching the inner edge of the disk where there is no more material to interact with. For some hot Jupiters, the migration stopped when the disk dissipated and left the planet stranded in its close orbit. What remains after migration is a system with a hot Jupiter close to the star, a largely empty inner region, and an outer system that has also been disturbed. The outer system disruption occurs because the migrating giant's gravitational influence extends outward as well. Objects in the outer disk get flung into the inner region or onto highly elliptical orbits that carry them from far out to close in and back. This rain of outer system material, bombarding the inner region of a post-migration system, can last for hundreds of millions of years. Any rocky planets that somehow survived the initial migration phase face ongoing bombardment from outer system debris stirred up by the giant's movement. The picture that emerges from migration theory is that solar systems hosting hot Jupiters are scarred environments. The inner regions are stripped, the outer regions are chaotic. Stable, nearly circular orbits in the habitable zone where liquid water could exist on a rocky planet, are essentially wiped out. For anyone hoping the universe is full of habitable systems, migration theory is sobering data, and it makes our own solar system look increasingly like a fragile accident. Our solar system looks simple from the outside. 1 star, 8 planets in nearly circular orbits, rocky worlds close in, gas giants further out, stable orbital architecture that has remained largely unchanged for 4.5 billion years, Earth sitting in the habitable zone at the right distance for liquid water, with a stable orbit and a protective magnetic field. This arrangement now appears to be the exception rather than the rule. Studies comparing our solar system to the thousands of confirmed exoplanet systems have revealed that our configuration is relatively rare. Most planetary systems discovered by the Kepler Space Telescope and its successor missions contain multiple planets packed closely together in tight orbits, often with no clear analogue to our outer solar system's giant planets. Many systems with detectable giant planets show evidence of the migration-driven disruption described in the previous chapter. The absence of a hot Jupiter in our solar system is itself statistically meaningful. Around 10 to 15% of Sun-like stars host a hot Jupiter detectable by current methods. Our star does not. Jupiter sits at its current distance, 5 times Earth's orbital distance, well within the range where migration could have occurred under different disk conditions. The fact that it did not migrate inward is connected to the specific mass ratio between Jupiter and Saturn, and the particular way our disk dissipated early in the solar system's history. The presence of Earth at a stable orbit in the habitable zone for 4.5 billion years required a specific chain of conditions. Jupiter had to stay where it was. The inner solar system had to avoid a migrating giant. The moon-forming impact, which gave Earth its large stabilizing moon, had to happen at the right time and with the right geometry to set Earth's axial tilt into a stable range. The axial tilt stability prevents extreme climate swings over long timescales. When scientists compare the probability of each of these conditions occurring simultaneously, the numbers get uncomfortable. Each condition individually might occur in a significant fraction of systems. All of them occurring together in the same system requires multiplying those probabilities together, and the result is a number that, while not impossibly small, points toward Earth-like stability being genuinely rare. The worlds we have examined in this video, a forming giant near the brown dwarf boundary, an inflated hot Jupiter scheduled for destruction, a massive planet orbiting impossibly far from its binary stars, are all examples of how violent, extreme, and unstable most planetary systems actually are. They represent outcomes that are common in the universe. We represent an outcome that may be uncommon. That does not mean habitable planets are unique. The galaxy has hundreds of billions of stars. Even a small fraction of systems developing stable habitable zones represents an enormous absolute number. But the easy assumption that habitable systems are ordinary turns out to be poorly supported by the evidence we have accumulated from exoplanet surveys. We are beginning to understand just how carefully calibrated our situation is, and the instruments being built right now will push that understanding further than any telescope has reached before. The James Webb Space Telescope launched in December of 2021. It reached its operational position about 1 million miles from Earth and began science operations in 2022. Its primary mirror stretches 21 feet across, about 3 times wider than the Hubble Space Telescope's mirror. Built to observe in infrared wavelengths, it was specifically designed to see through the dusty environments where stars and planets form. The dust that blocks visible light is largely transparent to infrared. Webb can peer into stellar nurseries and planet-forming disks and resolve structures that were invisible to every previous observatory. For the study of giant exoplanets like the ones we have covered, Webb has already delivered results. It has measured atmospheric compositions of hot Jupiters with greater precision than any previous instrument. It has detected molecules in exoplanet atmospheres that confirmed theories about atmospheric chemistry under stellar irradiation. It has produced direct images of young planets embedded in disks, helping scientists map the structures those planets are carving. For HD 100,546b, continued Webb observations over multiple years, will help scientists track whether the glow associated with the planet changes in brightness or position relative to the disk. Those changes carry information about the accretion rate and can help constrain whether the glowing region is the planet itself or the surrounding material. Beyond Webb, a new generation of ground-based telescopes is under construction. The extremely large telescope, being built in the Atacama Desert in Chile, will have a primary mirror nearly 130 feet across. At that size, its light-gathering power and resolution will far exceed any existing observatory. It is designed to directly image planets orbiting at distances similar to where gas giants sit in systems like our own, something current telescopes cannot do for most stars. The Nancy Grace Roman Space Telescope, a NASA mission scheduled for launch in the mid-2020s, will survey the sky in infrared and is expected to detect thousands of new exoplanets using gravitational microlensing. Among those detections, statisticians expect a significant number of massive outer planets similar to Rock's 42Bb, giving researchers a population of these distant giants large enough to draw meaningful statistical conclusions about their formation. Each new instrument expands the range of planet masses, sizes, and orbital distances that scientists can probe. The current sample of confirmed exoplanets already numbers in the thousands, but it is still biased toward planets that are easiest to detect. Large planets close to their stars are overrepresented. Smaller planets at larger distances are underrepresented. The next generation of instruments will begin correcting that bias, filling in the gaps in our census of other solar systems. As that census fills in, the mathematical likelihood of finding systems that resemble our own will become clearer, and the properties of the most extreme systems, the hot Jupiters, the forming giants at the brown dwarf boundary, the impossible distant worlds, will provide the boundary conditions that constrain every model of planetary formation. Somewhere in the data from these new instruments, there may already be something waiting that breaks the models again entirely. Density is the amount of mass packed into a given space. Iron is dense. A block of iron the size of a basketball weighs far more than you could easily lift. Styrofoam is not dense. A block of styrofoam the size of a basketball weighs almost nothing. Same volume, enormously different mass. To calculate the density of an exoplanet, scientists need two independent measurements, the planet's size and the planet's mass. Getting both requires combining two different detection methods. Size comes from transits. When a planet passes in front of its star, it blocks a fraction of the starlight proportional to the area of the planet compared to the area of the star. If astronomers know the size of the star from other measurements, they can calculate the diameter of the planet precisely. The depth of the light dip gives the size. Mass comes from radial velocity measurements. The wobble the planet induces in its star depends on the planet's mass relative to the star's mass. By measuring the wobble with a high-precision spectrograph and knowing the star's mass, scientists can calculate the planet's minimum mass. Divide the mass by the volume calculated from the diameter, and you get the density. For P67b, the transit measurements gave a radius slightly above twice Jupiter's. The radial velocity measurements gave a mass slightly below Jupiter's. Plugging those numbers in produces a density that comes out at a fraction of a gram per cubic centimetre. Water has a density of 1 gram per cubic centimetre. Styrofoam ranges from about 0.01 to 0.05 grams per cubic centimetre. The measured density of P67b comes in at around 0.05 grams per cubic centimetre at the low end of some estimates, comparable to styrofoam and lower than many published estimates of marshmallow density. This density is so low that the word planet starts to feel slightly misleading. The object has more in common with a very large, very hot bubble than with any solid or liquid world. Its outer layers are an extended, tenuous gas, held together by gravity at the centre, but diffuse at the edges. The reason this matters scientifically is that density tells you about internal structure. A dense planet has heavy material packed tightly at its centre. A low-density planet has light material spread across a large volume. Models of hot Jupiter interiors try to match the observed densities with proposed structures. A rock metal core of a certain size surrounded by layers of metallic hydrogen and then an outer envelope of molecular hydrogen and helium. For extremely low-density planets, the core must be small and the outer envelope immense. The inflation from radiation pushes the envelope so far out that the average density across the whole sphere drops to near atmospheric levels. Scientists testing different interior models against density measurements are essentially working backward from external observations to understand what a planet looks like deep inside, a structure they will never directly observe, and the visual extremity of what those structures look like from a distance, particularly as the star above begins its expansion, is something that combines everything we know about these worlds into a single devastating image. Picture yourself suspended in space at a safe orbital distance above P 67b. The planet fills a large portion of your field of view below. It is enormous, a soft-edged sphere of amber and copper-tinted cloud that stretches far wider than anything in our solar system. There is no solid surface to see. The clouds blend into haze, and the haze thins into the upper atmosphere without a clear boundary. At the edges of the planet's disk, where you can see the atmosphere from the side, a faint shimmer marks where the gas is escaping outward, the helium tail streaming behind the planet in the direction of its orbit, a ghostly ribbon catching the starlight and glowing dimly against the black. The star above is massive. Even at the planet's extremely close orbital distance, the star's disk appears perhaps 15 to 20 times wider in the sky than our star appears from Earth. It dominates the view. The light coming off it is not gentle. It has a slightly cooler, more orange tint than our star, because the host star of this planet is beginning the transition toward its red giant phase. It is already slightly expanded, slightly cooler at the surface, slightly brighter in total output. The planet completes one full orbit in 4.8 Earth days. From your observation point, the star sweeps across the backdrop of space in under 5 days. The rhythmic cycle of the planet's day side rotating into view and out again is absent because the planet is tidally locked. The same hemisphere always faces the star. The permanent day side glows brighter in infrared than the night side, and the temperature difference drives the supersonic winds you cannot see directly, but whose effects shape the cloud patterns visible below. As decades pass in your imaginary vigil, the star grows. Slowly at first, a fraction of a percent per million years, then faster as the stellar evolution accelerates. The star's disk in the sky expands, its colour deepens toward orange and then toward the red end of the spectrum. Its surface temperature drops while its total luminosity increases. More energy per second reaches the planet, even as the surface temperature of the star itself cools. The helium tail behind the planet brightens. More gas escapes per unit of time as the radiation intensity climbs. The planet's outer cloud layers shift in colour as different molecules become dominant at different altitudes under the changing radiation environment. When the star's outer edge finally reaches the planet's orbital distance, you would see the stellar atmosphere beginning to envelop the planet from one side. The boundary between the planet's atmosphere and the stellar plasma is not sharp, it blurs. The two atmospheres begin to mix. The planet's clouds dissolve into the stellar material from the star facing side inward. The planet does not explode, it dissolves. Over thousands of years, the dense gas of the planetary atmosphere blends into the vastly larger stellar envelope. The colours of the planet's disk fade and disperse into the surrounding stellar glow until the boundary vanishes entirely. What remains is a slightly more massive star. Somewhere deep inside its expanded envelope, atoms that were once part of a world twice the size of Jupiter are now part of the star above. The question of whether anything larger than this could exist without becoming a star itself has an answer that pushes the boundaries of what we call a planet. There is a ceiling on how large a planet can get. Mass is the key variable. As an object's mass increases, the pressure at its centre increases. Pressure generates heat. At some threshold of mass, the pressure and temperature in the core become sufficient to trigger nuclear fusion of hydrogen. the object becomes a star. It ignites, generating its own energy, and begins shining under its own power. For hydrogen fusion, the threshold sits at roughly 80 Jupiter masses. Any object more massive than that undergoes hydrogen fusion and qualifies as a star. Between 13 and 80 Jupiter masses, you have brown dwarfs. These objects fuse a form of hydrogen called deuterium, a heavier variant with an extra neutron in the nucleus. Deuterium fusion ignites at lower pressures than regular hydrogen fusion. It is brief and energetic, but the deuterium supply runs out quickly. Once it is exhausted, the brown dwarf can no longer sustain any fusion and it slowly cools. Below 13 Jupiter masses, standard models say no fusion occurs and the object is a planet. HD 100,546b, sitting between 15 and 20 Jupiter masses, sits above the 13 Jupiter mass planetary ceiling. If those mass estimates are correct, it is formally in the brown dwarf range. But the picture is more complex than the numbers alone suggest. Recent research has questioned whether the 13 Jupiter mass boundary is as clean as once believed. The boundary comes from theoretical models of deuterium fusion ignition, and those models depend on assumptions about the composition and internal structure of the object. Objects with different helium to hydrogen ratios or with higher concentrations of heavier elements in their cores might reach the deuterium fusion threshold at slightly different mass values. Some researchers have proposed that the relevant boundary should be defined by formation pathway rather than mass. A planet-sized object that formed through disk accretion around a star would be a planet regardless of whether it crosses the 13 Jupiter mass threshold. An object of similar mass that formed through direct collapse from a cloud of gas would be a brown dwarf. The problem is that determining formation pathway from current observations is extremely difficult. For any object approaching 80 Jupiter masses, the question becomes whether it ignites main sequence hydrogen fusion and becomes a true star. The smallest known true stars are red dwarf stars with masses close to that threshold. They are tiny, dim, and long-lived. A planet that gained enough mass to become a red dwarf would be unrecognizable as a planet. Its gravity would have compressed it into a sphere small enough to fit inside certain star systems while still sustaining billion-year fusion reactions. The largest confirmed planets, with masses around 15 to 20 Jupiter masses, sit tantalizingly close to where physics transitions from planet behavior to star behavior. The universe appears to allow objects in this boundary zone, but they are rare, temporary in their current state as they cool over time, and fundamentally different from both the planets in our solar system and the stars in the night sky. What they represent is something the universe seems capable of producing, but cannot sustain indefinitely, a brief, violent, glowing moment between one category and another. And what all of these extreme worlds taken together tell us about the future of planetary systems is the most unsettling conclusion of all. Everything we have seen across these 33 chapters points toward the same conclusion. Planetary systems are not permanent. They are temporary arrangements of matter, organized by gravity into structures that last for billions of years, but not forever. The planets we have examined, each extreme in its own way, are all at different stages of their journey toward an eventual end. HD 100,546b is at the beginning. Still forming, still feeding, still uncertain about what it will ultimately become. Its future holds either a slow cooling into a brown dwarf that will persist for trillions of years, dimming toward invisibility, or a reclassification into the planetary category as better measurements revise the mass estimates downward. Either way, the violence of its formation will eventually settle. The disk will dissipate. The accretion will stop. What remains will cool and stabilize over hundreds of millions of years into whatever final form it is capable of holding. HAT-P67b is in the middle stages of its end. The inflation is ongoing. The atmospheric escape continues. The star above it is already evolving toward the red giant phase that will eventually consume it. 150 million years from now, give or take, a world twice the size of Jupiter will cease to exist. Its atoms will become part of its star. The star itself will eventually exhaust its fuel, collapse, and leave behind either a white dwarf or a neutron star, depending on its final mass. The system will be unrecognizable. ROX's 42BB sits in orbit around two young stars that will themselves evolve over billions of years. As those stars age, their luminosity and size will change. The gravitational dynamics of the binary system will shift. The planet's orbital stability, currently sufficient but narrowly so, will face new stresses as the stars evolve. In the very long run, stellar evolution in the binary pair will reshape the entire system. And our own solar system is not exempt. Our star will exhaust its hydrogen core fuel in roughly 5 billion years. The same process that is already advancing in the host star of P67b will eventually unfold here. The expanding envelope of our dying star will engulf Mercury, then Venus. Earth's fate depends on whether the mass loss from the expanding star, which reduces its gravitational grip, allows Earth to migrate outward fast enough to avoid engulfment. Current models disagree on the outcome. Even if Earth escapes the expansion, the habitable zone will have moved outward long before that point. Within about 1 to 2 billion years, the gradually increasing luminosity of our star will push surface temperatures on Earth beyond the threshold for liquid water. The comfortable conditions that allowed life to develop over billions of years represent a narrow window in the history of our planet, one that is already more than halfway through. The universe is not a stable backdrop against which life unfolds indefinitely. It is a dynamic, violent, evolving system. Stars explode, expand, and die. Planets migrate, inflate, and dissolve. Even the most stable-looking arrangements carry within them the seeds of their own eventual transformation. What these giant, impossible worlds teach us is that the drama happening across the galaxy is not separate from us. It is the same story, told on a longer timescale, playing out in our own backyard. The only question is what we do with the window of time we have.